All right, then I will go ahead and get started on an application problem. This will be um, from section 1.5, and it will allow us to see how to approach this problem. I know we've got a couple of these types of problems in the homework, so it'll be good to be able to see that and know how to solve these. And then we'll do some inequalities. It should be pretty good. So what we have here is a problem with airplanes. We've got these B737s. Let me highlight some information here. We've got the B737s, and they fly at 517 miles per hour. We've got a Saab 340B that flies at 290 miles per hour. And then they create a scenario where there's a Saab that takes off, travels at its cruising speed. An hour later, one of the B737s takes off following the same route, traveling at its cruising speed. How long will it take the second plane to overtake the first? So let's take a look at what we've got here. We've got one airport, and the Saab takes off, and it is flying at 290 miles per hour. An hour later, we've got the 737, and it is flying at 517 miles per hour. And I know that's kind of a wiggly line. Maybe there was a side wind or something. I don't know. I'll make something up so it doesn't seem so bad. And now we need to figure out how long will it take. So this is talking about time. So we need some sort of relationship between time and the distance and the rate they're traveling. Well, it turns out that distance equals rate times time. This is a formula you will want to memorize. You usually see it written D equals RT. Distance, thinking about units we might use, this might be miles. Rate in this particular example is miles per hour. And if you multiply that by hours, we can see that the hours are going to cancel and we're left with miles. So it makes sense that miles equals miles per hour times hour. But that also highlights that we are going to need common units. So we will want hours for if we've got miles per hour, we'll want time in hours. Our distance will be miles and so on. We can do those conversions if we need to. So now we need to assign, let's see, we've got rate, that was given to us. So these are R values. We need time. We need to figure out distance. Well, 1 hour later, the B737 takes off. So the 737 is flying 1 hour fewer hours than the Saab. So if we say, let's let that equal T for the amount of time the 737 is in the air, the Saab will be in the air 1 hour more, so T plus 1 will be its time. I probably shouldn't use T for both of those variables, but I did. So the time that the 737 is in the air, we will call T hours. The Saab is in the air 1 hour more. It's not a bad idea to create a table or draw a figure when you've got an application problem like this. So a good table might look like this. We've got our plane, we've got some distance, we've got some rate, we've got some time. We've got the SOB is one of those planes, and we've got the 737 is the other. The rate of the SOB is 290. Rate of the 737 is 517. The time traveled for the 737 was t. The time traveled for the SOB was t plus 1. Now we need to figure out this distance, and I don't know how far they've traveled, but for the 737 to catch the SOB, they would have both had to travel the exact same distance. So I can just call that d. Now d equals rt. Oh, I should change that color so it's different from our table data. So d equals r times t. And now we've got two equations. Well, this d equals d of the SOB equals d of the 737. So that means I could go ahead and just distance of the SOB equals distance of the 737. The distance of the SOB is 290 times its time, and that has to equal the distance of the 737, which is its rate, times its time. And now we have a single equation with one unknown. We can solve that one. First, we will distribute the 290. So we've got 290t plus 290 equals 517t. Subtract 290t from both sides. And I've got 290. 517 minus 290 looks like 227. If I'm doing that right in my head, I'll double check with my calculator here. Yep, we're good. Now, divide both sides by 227 to isolate the variable. And I get, let's see, those 227s here will cancel each other out, leaving a 1. And I'm left with 290 divided by 227 is 1.277. I'm going to say 1.28. And I'm going to say is about equal to t. So it took 1.28 hours for the 737 to catch the SOB after the 737 took off. So the SOB has been flying for 2.28 hours. But that gives us our time, and that would be our solution. So with these application problems, I think it's a good idea, if you can, to underline or circle the things of import. I think it's a great idea to write a table or draw a picture. You need to recognize the formula we're using, and as it turns out, this particular formula is one that we will need to memorize. It's a good one to know. I do that little demonstration with the units to show that even if you forget the formula, looking at the units can really help you decipher what it is. But that helped us set up the table. So we had distance, rate, and time, and that table pretty well wrote the formulas for us. I didn't have to think too much once I had the table populated. And then it was just a matter of solving for t. Have you any questions on that?
Can we do one of the finance versions of this?
Absolutely. Do that one next. We did have a couple of finance questions on the homework, I remember. Let me do one of those. So here we've got an interest problem. Now the formula we'll be using here, now this is for simple interest, which this says we're using. And the formula we'll need here is that interest equals principal times rate times time. So I is the interest that we receive after a certain amount of time. As I said, P is principal. Principal means first amount. So I'll just go ahead and write first amount. It's the amount you would invest. It's the amount of the loan. It's the amount you charge on the card. It's that first little bit. R is rate, and this needs to be as a decimal. So we'll look at that here in a minute. We'll populate another table for this one. And T is time, and this would be in years. Okay, so we've got, let's see, what's the information we've been given here? 2 student loans. This is the total of the 2 loans. One loan is 5% interest, another one is 3% interest. So we've got 2 loans at 2 separate interests. They give us a 1-year time period. So there's our T. This 3% would be R, 5% would be another R. This would be principal for the sum of the 2 loans. So I'm going to call this P1 plus P2 to really highlight that we've got 2 of those. After the year, he owes this much in interest. So there's the I total, I1 plus I2. What is the amount of each loan? So let's go to our table. We've got 2 loans. So we've got one there. We've got principal. We've got rate. We've got time. And I'm going to go ahead and put interest over here on the end. I'm going to say we've got loan A and loan B. The interest rate on loan A will be 5%. So I'm just going to convert that to a decimal. The other one is 3%. Time in both cases is 1 year. So how do I get this principal? One of these I'm going to call, let's just call it P. And the other one will be, well, I know that both of these together have to add to 28,000. So let's just call this 28,000 minus P. So I'll put P amount of dollars in loan A and 28,000 minus P. Everything that's left goes into loan B. So the interest is principal times rate times time in both cases. And they told me that the total interest, the sum of those two, is 1040. So you can see how this table can help basically create our formulas for us. Now, looking at everything here in this right-hand column of the table, I could say, well, that means that 0.05p, which is just the product of those three for loan A, plus, let's do 0.03 times 28,000 minus p, again times 1, well, that equals 1040. So there's my formula. I need to go ahead and distribute this 0.03 through. So I've got 0.05p. 0.03 times 28,000 is 840. 0.03 times p is 0.03p. Can't forget the sign on that one. Okay, so now I'll subtract 840 from both sides. Combine my like terms, and I've got a couple of those have the same variable with the same exponent. 0.05 minus 0.03 is 0.02. 1040 minus 840 is 200. Now I'll divide both sides by 0.02. So those will cancel. 0.02 divided by 0.02 is 1. So I end up with 1p equals 200 divided by 0.02 is 10,000. Now P represents the amount in loan A. So loan A is going to get $10,000. Loan B gets 28,000 minus P, and 28,000 minus 10,000 is 18,000. So that's how much money is deposited in each of those accounts to get that total interest after a year. And the table really helped me. Now, I did have to memorize or use this formula. And that formula shows up on page 65 in the text. So that's one of those formulas you'll want to memorize because it shows up often enough. And this is, I think, a great way to approach these problems. Again, I circled everything in the problem that is of interest. I even labeled it. So these are the P1 and 2. That's the T. This is R1 and R2, and then the sum of the two interests. If I label that, it's far easier to get it plugged into the formulas as they need to be. And then it was just a matter of populating my table, which created my formula. And I think that will really make it a lot easier for solving these problems. Something I do want to mention is notice that the amount I plugged in was P. Later, we will be doing problems where we will have multiple variables. And I think it's a good idea not to just use X and Y. Because at the end of the problem, you will have X equals some number. But now you need to go back and figure out what in the world that X represented. And so if you label it, your variable, with something that makes more sense, then you know right away what it is you solved. Like later we'll be looking at, say, corn and soybeans, both of those, and how can we maximize those. So I might label one as C for corn and B for beans. And that way when I'm done solving it and I say C equals 5.6, I know that that's the corn. I don't have to go back and figure out did X represent corn or did it represent the soybeans? I just know right away. And so I would recommend that when you're creating variables, that you go ahead and use a variable that makes sense for the problem. And so I would suggest that you do that. I think it will help you when you're solving problems. All right. How are we doing? Do we have any problems or any questions on that one? Well, we've got an Amber Alert. All right. Let's take a look at a different sort of problem. And this one really, more than anything, is to let you know a particular notation or a term, and that is the term called a zero. So if we've got, say, the equation y equals 3x minus 4, if I want to graph that, what have I got? This is clearly in the form y equals mx plus b. So our b is -4, m is 3. So if I start here with the y-intercept at -4, and a slope of 3 means I rise 3 and run 1, that gives me the second spot on my line, and that would continue. I could rise another 3, run another 1, and that line will continue on forever. So we're good there. Now the question is, what is the zero of this particular function? The zero is an x-intercept. That's one way to look at it. It's the value of x when y equals 0. A couple different ways we look at that is it's the value we can plug in to the equation once the whole equation equals 0, lots of different ways. So let's look at this second one when y equals 0, and we'll just take that equation down and we'll let y equal 0. And we'll solve for x. So I'll add 4 to both sides. I've got 4 equals 3x. Divide both sides by 3, because again, we're isolating x. 3 divided by 3 is 1. And so we get 1x equals 4/3, which is 1 1/3. And if we see, that's pretty much where we're crossing the x-axis at 4/3. They may ask for an ordered pair, in which case we would type 4/3, comma 0. That would be the ordered pair. The 0 itself is 4/3. Later, we will be converting from factors to zeros and so on, and you'll get really used to that. But that term 0 will show up several times in the future. So I wanted to be sure you saw it now. It is in the homework, but I wanted to start talking about that now, at least introduce it. So keep that in mind. Okay, let's jump over to section 1.6, where we're solving linear inequalities. I should ask if there are any questions on that before we jump. Okay. 1.5, number 14. Let me take a look at that. Find the zero of a linear function. And that's essentially what we just did. So they had a slightly different problem, but that should be solved in the same way as we just did. So
I was just saying that's where I first saw it.
okay. Now they had it written slightly different. They had, I'll keep this same problem, f of x equals 3x minus 4. And what we're saying here is we have a function whose independent variable is x. And so we could also say the value of x when f of x equals 0. That's some notation that might be new to some. So you just replace f of x with 0 and solve it the same way it should work. All right. So let's jump to some inequalities. All right, one of the things that I usually do when talking about inequalities is I go through an exercise and I say 3 is less than 4. Is that true? Everybody says it is. 3 is less than 4. So I'll add 1 to both sides and I get 4 is less than 5. That is still true. Subtract 2 from both sides. I get 2 is less than 3. That's still true. So clearly I can add and subtract to both sides and everything's fine. Multiply by 4 and I get 8 is less than 12. That's still true. Divide by 2 and I get 4 is less than 6. That's still true. So clearly I can do the same sort of math that we've done before. So far the only negatives I've done were here. And that takes care of adding a negative is the same as subtracting. If I multiply by a negative 1, multiplied by a negative 1, I get negative 4 is less than 6, negative 6, I'm sorry. That's not true. That is not true. Negative 4 is not less than negative 6. Negative 4 is greater than negative 6. So this highlights that if we multiply by a negative, we have to reverse our symbol. If I go ahead now and divide by negative 2, I get 2. Let's keep that changed symbol greater than 3. Now that's false. So I'll have to reverse that symbol to keep it true. So if I multiply or divide by a negative, I have to flip that symbol around. A negative or a less than becomes a greater than, and a greater than becomes a less than. If I multiply or divide by a negative, I can do anything else to them, and it remains a true statement. So I usually start that way to show that this isn't much different from our formulas that we were solving. Let's take a look at one. 3x minus 5 is less than 6 minus 2x. And they want all of the solutions that make this true. So I will treat this kind of like an equation. I'll add, subtract, multiply, and divide on both sides to make sure that I isolate the variable. So if I were to subtract 3x from both sides, I'd have a negative in front of the x, so I would have to divide by a negative, and I don't like to do that because of that stuff we just saw. So I'm going to instead go ahead and add 2x to both sides. So I'm bringing all the x terms over to the left, which means I'd better move the constants to the right. So now I've got 3x plus 2x is 5x. Negative 5 plus 5 is 0. That's why I added the 5. keep my less than symbol. 6 plus 5 is 11. Negative 2x plus 2x is 0, which I wanted. Now I can divide by 5. We already saw that'll work okay. 5 divided by 5 is 1. So I'm left with 1x is less than 11/5. So I want all of the x terms, every single number that is less than 11/5. So in order to show that, I like to come over here and create a number line. So I'm going to say there's my 0. 11/5 is equal to 2 1/5. And I like to deal with mixed numbers when I'm on the number line. It just allows me to know where to put the dot. So come over, 2 1/5 is going to be right about there. Let's see. Why does there's my dot? Okay, my 11/5. All right. Now I want all of the numbers that are less than that. And on our number line, the smaller numbers are to the left, the larger numbers are to the right. So I want to be less than 11/5, not exactly equal to 11/5, but less than. So I might put an open circle around the 11/5 and then draw a line out here on top of my number line headed to the left, showing that I want all of those numbers over to the left. That works really well at graphing this. They also asked me to write interval notation, which is why that particular open circle idea is not the one I prefer. Let me do something real quick. I want to create another copy of this number line. Bring that down here so that I can show this other method. Okay, I still have my 0 here. Oh, wrong tool. Still have my 0 here. I still have my 11/5 right there. So another notation, rather than the open circle, is to put a parenthesis at that spot and then draw my line. Oh, not quite what I had in mind. Oh, it helps if you hold the right key down. All right. So there, now I've got this parenthesis, and that helps me with my interval notation. Because I want to start all the way over here on the left, and the smallest number you can think of times billions. I believe the technical term that I've used since I was 4 was a gajillion billion or something like that. So that's forever. It's not something we can really contemplate, but it's what we denote in math as negative infinity. And then we will put the largest number we are considering over on the right-hand side here, and that would be 11/5. When you don't include the number, you put a parenthesis, and notice that matches my notation for the number line, is to use the parenthesis. Now, again, if you can't get there, if it's not included, you put in a parenthesis. I can never get to infinity, so infinity will always get a parenthesis. If we were going large, say over that direction, we would go to positive infinity, which again would get a parenthesis. In interval notation, the smallest numbers on the left, the largest numbers on the right. So this would allow us to denote all of the numbers between negative infinity to 11/5, not including 11/5. That would be the interval that they would expect us to type. So if we were including, let me grab a different color here. If this were less than or equal, now we're including the 11/5. So I would put a bracket there and draw my line to the left. So my interval notation would still start at negative infinity, and it would still come up to 11/5, only now I'm including the 11/5, so it gets a bracket, and I can never reach infinity, so it gets a parenthesis. So if it says less than or equal or greater than or equal, you are going to expect some sort of bracket. And that's an example of using solving an inequality and then denoting that not only graphically, but also in interval notation. Now, a little word to the wise. I don't like to take, I think I've told you I'm lazy. I don't like to take my hands off the keyboard and reach over and grab the mouse. I know it's not very far away, but then I have to move the cursor down to that little palette, click on the infinity, and then come back up. As I said, I'm kind of lazy. On the keyboard, if you type \INF in your answer key, it automatically converts it to an infinity symbol. That's faster for me than reaching over and grabbing the mouse, moving it, clicking it, and going back. So sometimes I'll use that. If you forget this, you can just use now I'm going to say use your mouse, but go ahead and grab the mouse and hover the cursor over the tool. It'll give you a little tooltip, little pop-up that says \infinity. Now this backslash is the one above the enter key on your keyboard. There's another symbol we use because sometimes we not only go up to 11/5, but say we also want to have the numbers greater than 5. So I need to not only include those numbers up to 11/5, but I also need to include the numbers that are greater than 5. It gets a parenthesis because it's greater than, but I need to somehow combine those, and the symbol we use looks like a big U. It's not the letter U, it's a union symbol. Union meaning we're combining the two things. That symbol is on your keyboard. It is, if you're using, not on your keyboard, I'm sorry. Don't use the U on your keyboard. Use the U on the palette. If you want to use your keyboard to get it, you could do \cup, and that will convert over to the union symbol. Again, I'm lazy. I don't want to reach over and grab my mouse. It's faster for me to type cup. I've been typing for a number of weeks now, and so I do pretty well. But that's how you can type that union symbol. That lets you highlight that we have two regions on the number line that we need to include. And I feel like I'm throwing all kinds of odd things at you, but I wanted you to know this before we run out of time. We'll do one where we actually have to include the union symbol. But that's kind of background on how to type in these inequalities. Let's see if I can find one that has a couple of them. I just found one here.
Just real quick, what's the upside down one?
It's the intersection. It's where two things overlap. I find that we never use it in this class, interestingly enough.
Okay.
So you won't have to worry about it too much. When we do look at the intersection, we end up just typing between two numbers as a single interval rather than writing it as an intersection. All right, let's look at this one. We've got 2x minus 5 is less than or equal to -7, or 2x minus 5 is greater than 1. So they've given us this or case. I'm going to go ahead and solve both of them as if they were individuals. So now we've got 2x is less than or equal to -2, or 2x is greater than 6, I'll divide everything by 2, since that's the coefficient on x in each of these. And 2 divided by 2 is 1, so I've got 1x is less than or equal to -1, or still 2 divided by 2 is 1, 1x is greater than 3. So let's come over here to our number line. That'll be my 0. I need to look at -1 here, and I've got 3, which is right there. So I need the values that are less than or equal to -1. The or equal tells me I need a bracket. And draw my line out here. So that's the less than or equal to -1. Now I need greater than 3, so greater than gets a parenthesis. I'll drag that one out to the right. And so now I need the interval notation for that. The smallest number over here is -infinity, and that's going up to -1. So this will cover that left-hand section. -1 gets a bracket. The -infinity always gets a parenthesis. For this right-hand side, we start at 3, and we continue getting larger and larger as far as we can go. It's a Buzz Lightyear thing, to infinity and beyond. Infinity always gets a parenthesis. This 3 gets a parenthesis because it is greater than x. Now this or business. How do we handle that? Well, if I think about it for a minute here, if I, which often happens, what do you want for dinner? I hear that. Well, I'd like Mexican food or American food. Just throwing things out there. What I'm saying when I say that is that either Mexican food or American food, and when I say American, I'm like hamburgers, hot dogs. Mexican, let's say burritos or tacos. Either one would make me happy when I say that. Or when I say this or that, I'm saying either one will equally make me happy. If only one of those would make me happy, I would pick that one. But if I'm happy with either one, I would say or. So what we're saying here is either the numbers less than or equal to -1 or the numbers greater than 3 will satisfy this particular setup. Either one. So the ones over here or the ones there, either one would make me happy. So I'm going to just go ahead and take the union of those two. Now, let me change this up a little bit. I'm going to change colors so almost like we're getting mad. Let's put an and. So in my previous example, where I said Mexican food or American food will make me happy. Now, if I were to say Mexican food and American food would make me happy, what I'm saying is I need something from the Mexican food genre and something from the American food genre, or I will not be happy. It has to satisfy both of those. Now, looking at my number line here, is there any number that both satisfies less than or equal to -1 and greater than 3? There is not a single number that fits in both of those, so that would be the empty set. No solution. So in this case, because there is no overlap, there's not a single number that satisfies both of those. So the and gives me an empty set. No solution. Now let's switch it up just a bit if we can. I'm going to go ahead. I'm going to mess things up big time here. This was less than. This was greater than. I'm going to reverse those. So this will become greater than. That'll be greater than. This will be less than. So now let's look at this. I'm going to put this one on the second one. Let's ignore this for now. Still have my 0. We still have -1. We still have 3. Okay, now I need x is greater than or equal to -1. That's that section. X is less than 3. I'm going to do this one down below. That would be the second section. So the part that satisfies the left and the right is this section in here. That's the portion of the number line that is both greater than or equal to -1 and less than 3. So my solution in interval notation looks like that for the and when we reverse those. So that is the collection of numbers. Any number between -1 and 3, not including 3, but including -1, would satisfy both of those. So if I plug in, say, 0, is 0 greater than or equal to -1? Yes. Is 0 less than 3? Yes. So 0 makes this and this true. 1.5. Is 1.5 greater than or equal to -1? Yes. Is 1.5 less than 3? Yes. So that satisfies both. Let's look at 5. Is 5 greater than or equal to -1? Yes. Is 5 less than 3? No. So 5 doesn't satisfy both. It's not this and that. Now, 5 would satisfy up here because it does, since we had the or, it does satisfy this or that. Yeah, it satisfies the right-hand side. Boy, that's a lot of crazy stuff. Do you have any questions on these inequalities?
Number 3 on the homework in 1.6.
Let me take a quick look at that. Okay, let me do a snippet. We are at the end of the class time, so if you need to leave, feel free to do so. I'm going to go ahead and work this one because I like working math. But if you need to go, feel free. Message there. All right, we'll see you, Matthew. All right, so let's take a look at this particular problem. It looks a little lengthy, but we'll be okay. I'm going to distribute this. You know what? I'm going to FOIL this one on the right. First, go ahead and distribute that on the left. 6x times x is 6x squared. 6x times -8. 6 times 8 is 48, so that'd be -48x. Keep our less than. I'm going to keep the 3 right now. And I'm just going to FOIL these. So FOIL is first. 2x times x is 2x squared. Outside, 2x times -9 is -18. X. Inside, -1 times x is -x. And last, -1 times -9 is a +9. Okay, now I need to distribute that 3 through to all 3. Oh, you know what? I should combine those. -18 minus x is -19x. So that just combined those two. So I'll distribute that 3 through. So now I've got 6x squared minus 48x is less than times 2x squared is 6x squared. 3 times -19 is -57. 3 times 9 is 27. Now I can subtract 6x squared from both sides. Let's go ahead and add 57x to both sides so I can get all of the x terms on one side. Six x squared minus 6x squared is 0. So both of those are going to cancel out, which is nice. Negative 48 plus 57 looks like 9x. That'll be less than 27. Now I can divide both sides. That simplified a whole bunch. Divide both sides by 9. 9 divided by 9 is 1. I'm left with x is less than 27 divided by 9 is 3. So come over to my number line. There's 0, there's 3. We're less than it, so I'll put my parenthesis there and draw it to the left. My interval notation, start at the smallest number, which is negative infinity, extend up to the largest number, which is 3. It gets a parenthesis, just like my number line. Infinity always gets a parenthesis. So there's our interval notation, our graphical representation, and our solution in numeric form. Did that help?
Yeah.
Okay. Yeah, it was kind of weird because we had to multiply a lot together. We had an x squared, and it felt kind of like we were getting towards a parabola, but then those x squareds canceled and made it much easier. I was glad.
Yeah, it's kind of where I was kind of stumped for a second there, or worried, I guess.
And foiling that pair of binomials on the right-hand side really helps. It makes it a lot easier to just concentrate on that for a second, and then we could distribute the 3. All right. Well, now we're 5 minutes late. Hope you're not upset with me, but hopefully that was worth it. Any other questions before we call it a day? All right, I'm glad that
How do the tests?
Yep. How does the test?
Yeah.
I didn't hear the end of your question.
Oh, how does the test work?
Okay, it'll be a lot like a quiz. You'll take it in my math lab, just like the quiz is. You'll get one attempt. You won't get any of the help me solve this. And then after you submit everything, I will have a location in Blackboard in the assignments where you can upload your scratch paper. You can either take pictures of your scratch paper or scan it. You could put those pictures into a Word document or upload them individually. But then I will review your scratch paper and assign partial credit where it is merited. And then that will be your test score.
Okay.
I know that
So
sometimes we
it's
mistype.
in the math lab.
What's that?
It's at the college, though.
It'll be in my math lab. So wherever you access my math lab, that's where you'll do the test.
Oh, okay. That's
You
where
won't have to come in.
go into a test center.
Right. The test center, they've limited it to
Okay.
only those people taking placement exams, or there's one other thing, but they won't let me send online students to them. So we're just doing it in my math lab, wherever you happen to have internet access.
Okay, cool. And then would you recommend not going ahead?
No, I wouldn't recommend that. If you are comfortable and ready to go ahead, I would say go ahead and do that.
Okay.
If you have
I just wanted to
questions,
double check.
yeah, yeah, that's why I've got it all open now so that you can work on anything you want to. Our first test will be over chapters 1, 2, and 3. So you may not want to go ahead of chapter 3 before that first test so that you're not learning
Right.
stuff that you're not going to need for the test right away.
I
But yeah, if you want
mean,
to
that's the
start
one
working
thing
on,
I hate about math is like when you go back on problems, you're doing them differently, or you have to do it
sometimes, yeah,
once. And
yeah, we will learn things later that will make some of these first problems easier. And you'll say, why didn't you start me with this? And it'll be just because this foundation will help something else work better. But
right,
yeah, I in my engineering class, sometimes I have students want to apply triple integrals that they learned in calculus 3 when a simple algebraic solution is way faster. And it's kind of like, well, I know you know the calculus, but the algebra is so much easier. It's one of those things. It's how life seems to work.
right. Well, thank you so much.
You're
Appreciate it.
welcome. You're welcome. I hope everybody has a good weekend. Uh, we've got some heat coming up on Friday, but then it's going to get chilly and rainy. So be careful, whatever you do. All right. Have a good weekend.
You too. Bye bye.
Bye. See you Monday.